So this is another basic application for graph traversal algorithms. Now you might ask, Dan, what's a connected component? So let me draw you a picture of a graph just to kind of help you see what we're talking about here. So notice that I have one connected component, this one right here. I have another one right here, and I have another one right here. So we have three connected components. We have three connected components. So the question is, how many do we have? That's one thing we can ask. We can also ask or identify the connected components. So you might ask, Dan, why would we care about this? Now, a very common application for connected components is what we call segmentation. So sometimes this occurs in image processing, for example. So say, for example, I would like to have it where, say, each one of these, like if I imagine I took this graph and I imagine that was a picture, a grid of vertices and edges, where the edges represent connections between non-transparent parts of the image. So you can imagine I want to identify all of the things in the picture, so all of the separate chunks that I have in the picture. So segmentation in this very basic context would be I try to figure out which things are not transparent and which things are they. So I can identify each one uniquely with, for example, a number, so on its vertices and edges, for example. And that's one way you could use this, is you could imagine it as an image for image processing. You could imagine this, for example, if Say if, for example, we're talking about our friends in a big social network where there's a lot of interconnections between them. You can imagine I have, say, two friends. I got my Narwhal friend right here. So you say, hello, says hi to everybody. And I have my seal friend over here. Now, I would like to know if, say, for example, my two friends here, if they belong to the same social network or not, meaning the same part of the network. I should be a bit more precise. The same part of the network, such that if I wanted to find a chain of friends between them so that they can maybe invite some friends over and have pizza, that I'm able to do that. And believe it or not, answering that question is just like answering this question of which connected components do they belong to. So here's the catch though. So suppose that my Narwhal friend is up over here, and I say, hey, look, this is connected component number 1. And all of these edges and vertices, they're part of connected component number 1. So my Narwhal friend is in connected component number 1. So this is the bucket for connected component number 1. Now, suppose that my seal friend is in this connected component. Now, just for the sake of ease, I'll label this as connected component number 2. And say this is connected component number 3. So imagine I'm going to number the edges and vertices with number 3. So I would have my seal friend maybe in this bucket representing connected component number 3. And if I were to ask, hey, look, can my Narwhal friend, does this Narwhal friend have a sequence of friends, or at least say the friend of the seal? Is there some way that these two are actually part of the same network? And unfortunately, they are not friends among the same network, at least if we're talking about the connected components, right? Does everybody see that? So if I look at my Narwhal friend doesn't have any friends in common with my seal friend, right? Because they're way over here. What I could do now is if ever I wanted to say, come along in my graph, and I wanted to say, hey, look, I have this friend, and I have this other friend. Can they have friends in common with each other? I can ask my Narwhal friend, hey, look, I'm in connected component number 1, and my seal friend can say, I'm in connected component number 3. The answer would be straight up, no, they do not have any friends in common. Pretty neat, right? So that's one way you can use connected components. So the way that we're going to do this here is we're going to assume that our graph will have these numberings as an extra attribute that we can keep track of with each vertex and each edge in the graph. However, you can easily modify the ideas we talk about here to store, say, a list or some other data structure that has this information baked right into it. But there's many, many, many different applications for connected components. That's just one example of something you can do with connected components as soon as you identify which part is with which. So let's talk about this. So let's assume each vertex and edge can be numbered. And the next thing is that DFS and BFS with a starting vertex or source vertex, has a traversal that processes all vertices and edges reachable from it as in the starting vertex. So you might say, Dan, what are you going to do then? Well, we're going to use the same idea that we had from testing if a graph is connected or not, which in that case, we picked the vertex, we ran DFS or BFS, and then we can determine if there are more connected components or not. If a graph only has one connected component, it must be connected, right? So if we take and we have it where we have multiple connected components, what we could do is we could just simply number each vertex and edge by adapting one of these two traversals so that every time we encounter a new vertex or edge that's a part of that given traversal, we can number it uniquely. So that every time we start up DFS or BFS again with another starting vertex, we assign a new label or number, as we're going to say here. So let's see how this plays out, everybody. So the whole idea is that I need to make sure I label the vertices and edges uniquely among each connected component. So I could say if I grab you one vertex here, I should be able to tell you this is in connected component number 1. Just like when I had my narwhal friend and my seal friend, I should be able to tell you that these two people are not, or I say animal friends, aren't actually friends with each other, right? They should be able to tell you that they belong actually to two different ecosystems, I guess. So let's see here. So let's put this all together. Sorry, I'm getting very excited here. So what we're going to first do is we're going to adapt the same idea that we had previously from our test for connectedness. Except what I'm going to do is I'm going to start off with a number. And every single time I run DFS or BFS, I'm going to increment this counter by 1. So I have a unique number each time I invoke it. And then I'm going to have it where I modify one of the two traversals such that I pass along this number. And every time I'm going to encounter a new vertex that gets marked and a new edge that just gets labeled, I'm going to number it. Okay? So this is in the most purest sense, I'm literally going to adapt these two types of traversals in a specific way. But also I want to do this in a way such that you could still apply BFS or DFS without any modification. So all we're going to do is we're going to add this extra attribute in so that it's no different than DFS or BFS, with the exception that we're going to focus in on this numbering, okay? So we're going to have, our algorithm is going to be called comp with 2 N's. And it's going to take in the graph. And as input, we're going to get a graph G. And I must stress that the number, it's assumed that the vertices and edges are able to be marked and labeled respectively, and that the edges and vertices can be numbered. They can be assigned a unique number like in our example over here, based on their connected component number. Output is going to be to identify, so it's not going to actually return anything other than it's going to modify the graph. It's going to change these attributes on each vertex and edge. Identify connected components. That's what it's going to do. So you can have the cleanup phase at the beginning of this algorithm if you'd like. I'm just going to, for the sake of brevity, just straight up cut right into the whole process that we had, just akin to a previous example we did. So we have a variable I'm going to call comp num, which is going to be the component number. We're going to assume that the first connected component is labeled 1. So like in our example here, I started off with 1. And then we're going to go through for each one of the vertices. For each vertex v among the set of vertices, we're going to do the following. We're going to check if v is not marked. If it's not marked, what did we say? It means that there's another connected component out there. So if v is not marked, sorry, that looks like an R. If v is not marked, then you're just going to update our, sorry, instead of updating, let's just first run connected components or comp. We're going to run it with vertex v, and we're going to give it that number that we currently have, comp num, and then we're going to update comp num to be incremented by 1. So comp num is going to be comp num plus 1. And that's the end of the if statement, and that's the end of the for each loop. And there you go. So you might ask, okay, so what's this now? Because it takes in a vertex and it takes a number. So now this will ensure, so I must stress, just to really stress this point, and we've seen this when we talked about testing connectedness of the graph, is that if the graph is connected, every one of the vertices and edges will be labeled with a number 1, okay? So they'll be numbered 1. However, it's disconnected, it means it has more than one connected component, so this may get run several times. The point is it doesn't change the overall nature of a depth first search traversal or breadth first search traversal. In our case, I'm going to adapt DFS, okay? So let's see how this is going to work out. So we're going to adapt DFS. Just to keep this really simple, I'm just going to say adapt DFS, because I think I got the core idea across. So here we go. So here's the algorithm. We're going to give it the same name. I know, Dan. You're funny. It's going to be called comp, except the parameters for it are going to be different, which means it's okay for me to do this. So I'm going to have a vertex u and a number called comp num, akin to what we just said over here. So I'm going to skip over the input and output, but it's going to identify the connected component for vertex u. So all the vertices and edges that are reachable from vertex u will be numbered comp num. So what's the first thing we always do in a depth first search? Well, we mark the vertex, and then now I'm going to introduce this numbering. So I'm going to have a function that's going to be number. It's going to take in a vertex, and it's going to apply a number to it. That's what number will do. So it numbers vertex. So it numbers the vertex. That's all it does. There's nothing else. It's just like a one-liner in there. So next, we ask, well, we don't ask. We just simply go through each one of the incident edges, just like we did before. For each edge UV, we're going to do the following. We're going to check if the edge UV is not labeled. If UV is not labeled, then we better do something. Then, because it's not labeled, I'm going to number it now. So we're going to number it. So I'm going to have another function called number. It's going to take in an edge, and it's going to take in a number. So I'm going to give it U, V, and it's going to be comp num. So all this is going to do is number the edge. There's nothing magic going on here. That's all it is. It's like a one-liner. That's it. There's nothing scary or anything happening inside of this. It's just some constant amount of operations that happen here. So it numbers the edge. Then we just do the same thing we did before. If V is marked, then what we do is we label UV as back edge, right? Otherwise, we're going to label UV as discovery edge or forward edge. That says discovery, by the way. The V and the E and the R sort of melted into each other like it went in the microwave, like microwave cheese that went a little too long. And then we're going to apply comp with V, and we give it comp num, the same number. We don't change the number. The only time we change it is when we have a new connected component. Yeah, exactly. So we just run it like this. This is it's not much different really at all to how DFS was originally set up the way I had it before. Just now I have this numbering going on. And I just renamed the function. And there you go. So all I did was I took DFS and I just tweaked with it ever so slightly. So I added this additional behavior to it. So with this, I can number my connected components so that all I have to do is if ever I pick up a vertex, I can say, hey, look, which connected component do you belong to? I'm number 1. Or, like my Narwhal friend says, I'm number 1. And my seal can say, I'm number 3. The point is that it gets. I'm encouraging you to think about the graph not just as just a graph, but also as something that you can use as a tool for modeling all sorts of different things. But yeah, so this is one way you can use connected components. You can help you organize chunks of your graph so that you know which part belongs to which part. Just like if you imagine these as, say, neighborhoods in the most literal sense, like here's a bunch of houses. I don't know, I'm like Godzilla here. I'm just like, I'm just coming over here. And this is one neighborhood, that's another neighborhood, this is another neighborhood. I should be able to tell you if I smash this neighborhood, but I leave this one free, okay? So, anyways, that's how you can this is how you can compute connected components, everybody. Sorry, I'm getting really excited here. Hope you thought that was pretty interesting.